Harry Bennett's going to give the final presentation and talking about an eclectic mix of challenges that the Buccaneer mission has had. Thank you.
Thanks very much, David. And I apologise in advance. I don't have the great mission logo of the Buccaneer Pirate on my presentation. I should have included that. But good morning, everyone. My name is Harry Bennett. I'm a space system engineer with Defence Science and Technology Group, and today I'm going to be discussing some of the space environment testing approaches for satellites. So I'm by no means a world-leading expert on the topic, but our team at the Space Operations Group have learned some valuable lessons through the Buccaneer program, and I thought it would be valuable to share some of those with you and what we're thinking about and what we're currently executing as part of our space environment testing campaign for the Buccaneer Main Mission, and what we're thinking about as well for the future. So like David discussed before, our program has its origins in the Buccaneer Risk Mitigation Mission. Buccaneer Risk made use of a number of facilities, both in Adelaide and around Australia, to achieve confidence in flight-ready spacecraft for defence needs. This included our partnership with the University of New South Wales, Canberra, the AITC, the Advanced Instrumentation Technology Centre at the Australian National University, and facilities and staff at DST Group in Edinburgh and around Australia as well, to support what we wanted to create for a successful mission. So this provided an excellent foundation for us to think about for the future, for delivering space-based resilient systems to the Australian Defence Force. And thinking about some of these key points I have listed here about what that might look like in terms of capability and infrastructure that we have in Australia, what we currently have, and some ideas and some future concepts that we can undertake or we can explore more in the future. So now onto the fun part, the space environment. So I apologise for and with a very rich space background, but I'll just dive into some general concepts about the space environment that we consider about and we think quite deeply about here at DST. So satellites experience such a harsh environment in low Earth orbit, as well as on launch en route to low Earth orbit. Understanding this space and launch environment is paramount to ensuring the survivability and performance of your space mission as it's executing its mission. I like to draw a distinction here between the natural and the unnatural space environment. Some of the challenges satellites have in the natural environment include the high level vacuum environment, thermal cycling, thermal extremes related to the on-orbit vacuum environment they experience, radiation, charged particle radiation from the sun and galactic cosmic rays are some examples as well of how radiation can affect electronics and hardware on board. Here I have what we call a charged particle map, and that area in red is famously known as the South Atlantic anomaly, and it is for sure problematic for spacecraft communications. It's an unnaturally weak spot in the Earth's magnetic field, and comms, onboard computers, and satellites will experience serious issues due to radiation in this region. So it's something we have to think about, and something that encourages us to think more about the testing regimes we undertake for these missions as well. There's also the unnatural element, of course, and I think as Professor Boyce pointed out earlier, the rocket launch, the vibrations that are introduced from launch are something that we must also take into account in terms of our vibration testing, and the shock alone is something quite terrifying. And a really relevant news piece here that I think hits home about the dangers of testing with satellite missions is what happened recently just this year with a geomagnetic storm introducing and flying the field around the Earth that caused so much drag to be introduced to 40 of the 49 Starlink satellites that they were forced to deorbit. So it serves as a potent reminder of what the threats we face if we're to have successful defence space missions for the future. So what we've been doing at DST is one of our key acquisitions has been a thermal vacuum chamber for testing. So spacecraft transition from complete darkness in eclipse to full sunlight, ranging from negative 150 degrees to positive 150 degrees Celsius. So how's that research engineering at DST Group? We have an Australian designed, manufactured by Mechanica company in Melbourne, Victoria, to do some of this thermal testing. So the testing is four key areas that I'll discuss briefly. Is thermal cycling, necessary to evaluate the survivability under the thermal environment. The thermal bakeout, so sterilizing that satellite or satellites or payloads before you launch them on orbit. Outgassing requirements. To measure and understand those outgassing effects is also a really key consideration before a satellite is sent into orbit. And then also thermal balance testing is just one of the other really concerned areas that we think actively about before we want to launch any kind of defense mission. And just on the right there, that's the complete TVAC setup, of which there's a few liquid nitrogen chambers behind there that I've had the pleasure of seeing the frost. It's always cool. So I mentioned vibration testing. So this is really fundamental. So we have a Brule and Care, if I've said that correctly, apologies, I think it's Neuden, testing vibration table, housed that DST group as well. So what we can see here is the Buccaneer Main Mission primary payload on this table. And there's a number of different testing. We've got the results here for the random profile that we have, but also another key area is fine sweep testing. So I think between 5 and 100 hertz, if I've remembered correctly, of sweeping the different kinds of vibrations that can be introduced to payloads and to the satellite itself. That's really important for us to conduct because we don't want our payload to shake apart during launch. It is really a key concern, and it's again a potent reminder of the dangers that the unnatural space environment introduce to a space mission. So radiation testing. So particle radiation can disrupt electronics through single event effects and introduce all sorts of displacement damage onto onboard computers, onto the electronics, the really sensitive electronics and instrumentation that we have on satellites as well. UV radiation, like atomic oxygen, can erode the materials, the optical materials, the mirrors itself. And this thermal and electrical properties can be affected for the long term, which can end a mission. And we believe it has, of course, in the past, ended missions from radiation effects alone. So we have collaborations with ANSTO, the Australian Nuclear Science Technology Organisation, at Lucas Heights. The Australian National University's Heavy Ion Accelerator are just some of the key capabilities that we have here in Australia that Defence Science Technology has been working with to understand and conduct some of this testing for our mission. I'll touch on now one of my favourite areas, attitude, determination and control. So satellites are equipped with ADCS, attitude determination and control systems, or attitude, also known as attitude orbit control systems, which control the orientation of the satellite, and they are inherently complex. They have a number of mechanical components in the form of magnetometers, typically reaction wheels as well, and the determination sensors to inform that control action. That makes them quite sophisticated pieces of kit. And we want to be able to test those as best as we can on the ground before we launch those on orbit. So they're inherent for a key task typically when they're launched from a launcher is known as detumbling. So normally they're in some kind of a spin arrangement that we have to stabilize. And it's really vital that that is undertaken first and foremostly for most satellite missions in order to achieve mission objectives, to get it to a state where you can control that position and control the pointing requirements. And those pointing requirements are vital for certain defense missions, of course. So how we currently are undertaking this, and this is a tried and proven technique, is through hardware in the loop simulation, so hardware in the loop testing. So we take the attitude, determination and control system of the satellite in a lab environment and we effectively plug it into a software simulation. So that software simulation spoofs or creates artificial sensor readings for the determination aspect of the control system. And from that we can try and simulate how that is also done. And with our key partner for the Buccaneer Main Mission, with Innovative Technologies, there's also very extensive pure software in the loop and software simulation being done of representation of the model of the satellite itself. But one capability we currently do not have at DST is a full physical attitude, determination and control test facility. So what we are lacking at this point is what we would like to do is simulate on the ground as best as possible in a Helmholtz cage, with a solar simulator, star field, and air bearing table. These are some of the ideas we're throwing around at DST at the moment about how we could best assess pointing requirements and other control requirements that may be necessary for defence missions in the future and going forward. So we've currently purchased an bearing table as part of the first stage of exploring this, and it's something, and there's a capability we would really like to see on offer in Australia as well. And just one hypothetical use of such a facility is undertaking a de-tumble scenario or process for the satellite. So being able to reliably assess that and then conduct advanced research for new types of guidance navigation control algorithms, like potentially advanced constellations moving forward, not just one satellite, but multiple satellites on orbit, it will be something really important to us that we think is vital to space mission requirements going forward. So just to wrap up, that's some of our key ideas of where we're looking at in terms of space environment testing at DST and where we're thinking about in the future about how we can create those resilient missions in terms of how best can Australia and how can best we at DST have that capability for reliable environment testing and where it might sit for the future. That's just a quick summary for me today. I'm happy to field any questions if time is permitting. And yeah, thank you.